Welcome back. This lesson, we're going to take a look at the NUMA architecture in vSphere. In this lesson, we'll explain how the ESXi hosts are NUMA aware, explain the virtual NUMA topology, otherwise known as vNUMA, and describe how to optimize the number of cores per socket in a VM. So let's first take a look at what do we mean by NUMA, right? It stands for non-uniform memory architecture, as opposed to uniform memory architecture. In traditional computing systems, you might have had a system with more than one CPU socket with multiple cores inside each of the different sockets, but you might have had one central memory bus that has access to all of the host's main memory. So no matter where a process is running, no matter what core, no matter what socket, access to memory would have been a uniform process. In non-uniform memory architecture, like we see here in our example, there are essentially dedicated memory banks for each of the different CPU sockets. So for instance, if you have the socket with its local attached memory compared to the socket, another socket who has its own attached memory, if a process is running in one socket, it may access memory within that same socket. It may need to access memory from another socket. Therefore, you have a kind of a distinction here between local access to memory versus remote access to memory because of the distance in terms of the buses that are used on the compute system to gain access to those memory banks. And so you end up having a non-uniform memory architecture. Every operating system has to be able to be aware of this type of environment. And you'll find NUMA environments are the common standard these days. They actually allow for a much larger scale in terms of cores per socket and multiple sockets per host, so that it's going to be the standard for pretty much any compute platform these days. In fact, it's been the case for all of AMD Opteron processors. They've always been NUMA based. And then on the Intel side, for at least x86 and x64 processors, they've been NUMA since the Nehalem processor. So now over 10 years of pretty much standardized on NUMA environments. So now the ESX server, of course, will need to be NUMA aware as well. And it's been for many, many years. And what do we mean by that? Well, when a VM is scheduled, first of all, the ESX server is going to look at the NUMA environment and look at the CPU sockets with their locally attached memory banks. And each socket with a local attached memory bank is known as a NUMA node. So in our example here, we've got two NUMA nodes, right? Two sockets, each socket with their own locally attached memory banks. When a VM is powered on in a NUMA environment, the VM is essentially assigned a home NUMA node. So here, VMs 1 and VMs 2, they've been assigned a home NUMA node for the NUMA node on the left, and the VM3 has been assigned a home NUMA node for the NUMA node on the right. The significance of that is that for the purpose of providing the best scheduling and memory access, for VMs 1 and 2, their memory will be placed by the ESX server on the memory banks that belong to the NUMA node on the left, so that those VMs will always have local access to their memory, and the VM3 with its home NUMA node over on the right NUMA node, its memory will be placed in the memory banks on the right hand side of that. So each VM will each be assigned their own home NUMA node. In fact, all of the virtual CPUs of each of those different virtual machines will always be co-located, and all the worlds for each of those VMs will all be co-located into their home NUMA nodes. This promotes as much local access to memory as much as possible. This is different than what it was with when you had a uniform memory architecture. When you had a uniform memory architecture where you might have had two sockets all accessing the same bank of memory, or at least the same bus to the banks of memory, because it was uniform access, it didn't really matter where a VM was running, the memory is always uniformly accessed. So in those environments, VMs who had multiple CPUs would actually be the system would distribute the virtual CPUs across all the sockets to get the greatest potential scheduling opportunities as much as possible. But with NUMA environments, a VM is going to be set up with its virtual CPUs always consolidated within a home NUMA node. Now, VM can actually change home NUMA nodes if it turns out that the NUMA node on the left is having its CPUs becoming overly utilized and there are more free CPU cycles in the other NUMA node. The system will consider migrating one VM and all of its virtual CPUs to the other NUMA node, and it will eventually copy its memory over to the other NUMA node to again promote as much local access to memory as much as possible. So The host is a NUMA-aware VM kernel, right? We support this mechanism to provide optimization for getting as much local access to memory for each of the different virtual CPUs for each of the different virtual machines. And like we mentioned, the VM kernel will schedule dynamically, balancing the processor load to attempt to maintain that balance. Now, a couple terminology here, just to make sure we already understand how these things all work. And in fact, when you're using a tool like ESXtop, ESXtop will actually use terms that we find here. For every virtual machine, they will always have at least one virtual socket, right? The VM is going to be created with a virtual motherboard with virtual sockets, and then those virtual sockets will have one at least virtual CPU. And if you assign a VM with one virtual CPU, it'll certainly have the virtual CPU within the virtual socket. The VM kernel will then map that to a pCPU. It stands for physical CPU, but it's really just a VM kernel construct. Where the VM actually is scheduled, though, is on either a CPU core or maybe onto a hyperthread. It all depends on what's happening on that ESXi server at that point in time. We tend to think the hyperthreads are the great place for the scheduling of the different worlds because they give us the greatest levels of flexibility in terms of scheduling. But if it turns out that the CPU actually has more free cycles, a pCPU may be mapped to the entire core. Now, of course, this also depends on how you've assigned the scheduler on your ESX server. The default scheduler, which we talked about in the previous lesson, will map the virtual machine's pCPUs onto hyperthreads, and virtual CPUs will be spread across the core. So for our example over on the right, our third VM, he's got two virtual CPUs. Those two virtual CPUs will be mapped to individual pCPUs, and they all get mapped to different cores. That's by design, right? To give the VMs the greatest level of potential concurrency in terms of its scheduling by giving each of the different virtual CPUs their own dedicated cores. However, due to the side channel attack issues, you have these other options, right? If you had set the side channel attack or the side channel awareness version 2, in that case, those two virtual CPUs would actually more likely be scheduled on two hyperthreads of the same core, right? The default scheduler wouldn't do that, but the side channel aware version 2 would potentially do that. If you had side channel version 1, well, in that case, yeah, the second hyperthread on every core is effectively disabled. So every virtual CPU is scheduled on different cores by design. Any case, that's what we're seeing here. The VM kernel will map the virtual sockets, the virtual CPUs with the virtual sockets to these pCPU constructs. I bring that up because when you use ESXtop, it will actually show pCPU metrics as well. So that's what it's referring to. It's referring to this VM kernel layer. Now, another important part about being NUMA aware is the system will also create for each VM one or more NUMA client. Basically, since the VMs all have at least one virtual socket, how is that VM going to be presented access to memory? Is the VM going to be accessing memory where the VM is actually made to believe they're in a uniform memory architecture? Or is the VM to be made to believe they're in a NUMA architecture? That really all depends on a few factors. But as you can see here, in each one of these examples, the VMs are being presented a single NUMA client. Each VM is basically being made to believe they're in a uniform memory architecture, which they should be, especially VMs 1 and 2, right? They both have one virtual CPU in one virtual socket. They should always have one uniform memory architecture. It should always be local access to memory for those virtual CPUs. But VM number 3, he's got two virtual sockets, right? Two virtual sockets, each virtual socket with one virtual CPU in it, with one NUMA client. So again, this is actually a VM who has two sockets with one uniform memory access model. So the VM3 actually is made to believe they're in a uniform memory architecture, even though they actually have two sockets. Should the VM be told they're in a NUMA environment? No, not necessarily. These two virtual CPUs of the VM will be placed in the same NUMA node on the ESX server, so it is a uniform memory architecture by design for that VM. So that is our first intro here. We'll take a quick break. We're going to dive a little bit deeper into the NUMA and vNUMA architecture after this break. So we'll see you in a few minutes.